Hello students, let's continue with the lecture. So we have seen that net force that is applied in any direction is equal to net change of momentum in that direction. With this, we have found out the resulting force that was acting on the control volume by the plane is equal to Fn, and the force that is exerted by the jet on the plate will be equal in magnitude of Fn but opposite in direction. That's why I have used minus sign here. Now this Fn is in fact the force exerted by the jet on the plate, which will be in this fashion. Further, we have also discussed that if the discharge is flowing in a proportion that is not in an equal proportion, then the ratio depends upon the theta, and which is given by q1 divided by q2 is equal to 1 plus cos theta divided by 1 minus cos theta. In this entire problem, I have resolved the forces into pxs and nxs, right? But you can do it in other method, that is by resolving the forces in absolute x direction and y direction, completely ignoring nxs and pxs. Here whatever I have just said is mentioned here. Similarly, all the forces and the velocities can be resolved in absolute x direction and y direction to calculate the force exerted by the jet on the plate. The force exerted by the jet on the plate will be equal in magnitude and opposite in direction to the force exerted by the plate on the jet. This is important. Please understand this. Let's continue with this. Now, for a small experimentation, what I did is I took a discharge of 15 liter per second and the diameter of nozzle of 50 mm, and I tried to vary the angle theta like this. So here the theta is increasing and suddenly it is becoming 0. See, so I have taken the theta from 0 radian to pi radian. It's 0 degree to pi degree, pi radian. Okay, 0 degree to 180 degrees. So complete flat is 0 degree. Again it will become vertical. Again it will become completely flat, which is 180 degree. So then I've written a simple Python code. From this you can understand that the force increases with the increase in theta, okay, and it reaches a maximum value when the angle is exactly pi by 2 radian, that is 90 degrees. So if the plate is absolutely vertical, okay, if the plate is absolutely vertical, the force exerted by the jet on the plate is going to be maximum. That's what's given by the curve here. And why it becomes maximum is because sine theta, sine 90 is 1, so force would be equal to rho q v. So v will be the exact component in x direction, so then this will be maximum. So this is a small experimentation. There is a code, Python code available. You can try for yourself. And with this, let's solve the problem. The problem is the water is discharged from 50 mm diameter nozzle of a fire hose at 15 liter per second, figure A. So there's a nozzle, it is discharging some water, it impinges on this plate which is dividing the water, okay, and there's it's going out from here, it's going out from here. I hope the image is clear to you. The flow strikes the plate surface such that 3/4 flow along B. So here along B, so this is B, it flows 75% of water flows from this direction, while remaining 1/4, which is 25% of the water, flows from this direction along C. Determine x and y component of the force exerted on the surface. So we are asked to find the component of x and y force component in x and y direction exerted by the jet on the plate. To analyze this, we start by drawing a control volume. Okay, so there's the control volume here, and velocity that is coming in. This is the velocity that is coming in, VA. That's what the direction of velocity going out. It's absolutely 90 degree. This is velocity C that is going out again. And here there is a resultant force acting on the control volume because it is impinging on the plate. Okay, so the force we are interested, or the force that we are going to calculate, is not this force. The force that we are interested is the force that is going to be exerted by the jet on the plate, and it is going to be equal in magnitude to this force, which I have written as Fn, but opposite in direction. So the angle that makes the horizontal VC mixed with the horizontal 60 degrees is also given. This is also given. Now you can break this into X and Y component. Similarly, the force also you can resolve into X and Y component. Incoming velocity also you can break into X and Y component. And with this, let's try to solve the problem. So along the x-axis, okay, along the x-axis means absolute x-axis. For your reference, there's a figure here. So net force is the change of momentum in that direction, which indicates forces in x direction. There's only one force, that is f of x is equal to net change of momentum in x direction. So we have already seen that. So force is equal to momentum flux that is going out of the control volume minus momentum flux that is coming into the control volume would give us the force, right? So let's say now here's minus f of x, minus because it is in negative direction. The sign convention is very important when you analyze vectors. Okay, so minus f of x is equal to what is going out. There are two things going out from here and from here. So the thing that is going out, the momentum that is going out of this place is rho density QC times VC. So VC, not just VC, but VC cos theta, because this is the direction in x direction, minus, and this is the component of this is the momentum in x direction that is coming into the system. So x direction will be mass into velocity in x direction. Mass is rho into qa. So qa is nothing but the total q times va cos theta. So this is our entire expression. From here we get that the force, we also need to understand that the Q, capital QA, is 15 by 1000 meter cube per second, and similarly the QC is the QC is nothing but it is the 1/4 of QA. So by substituting this QA and Q here, what I have done is I have substituted the value of QC, and then I have taken out QA, and further I have calculated the value of f of x. Now this f of x is 66.70 Newton. Further, along the y direction, resultant force is equal to change of momentum flux in y direction. Similarly, in y direction, let's see, that is going out of the system in y direction. This one, right? Rho QC VC sine theta positive, and rho QB VB negative because it is going in negative direction, minus this is what is going out of the system, minus is this minus. Now rho Q, that is coming into the system. Now this is coming into the system, but it has a I mean the direction by sign convention it is in negative direction. So that's why I have put negative sign here. So here I have mentioned it. Please take care of the sign conventions. Okay, we have to be very serious with the sign conventions, or else our analysis will be wrong. So here, similar to what I did in x, I am also doing the same thing in y, and then I'm calculating the value of y, f of y. Now, one thing that we need to understand is whatever the force that you have calculated right now is the force exerted by the plane on the jet. The question is asking us to find the force exerted by the jet on the plate. So how to end? I mean, this is the answer, but the interpretation is the force exerted by the jet on the plate will be equal in magnitude but opposite in direction to the force that we just calculated. What did we calculate? We calculated the force that was exerted by the plate on the jet. So now equal in magnitude, right? Magnitude is same but opposite in direction. So f of x, we have taken it this side, right? So it's going to be this side. So we opposite in direction. F of y, we have considered this direction. So the value remains same, magnitude is same, the direction is opposite. So this is the solution that question is asking us to find. Let's continue with the next. Here we have, instead of a flat plate, we have a curved surface, and the water is getting impinged on the surface from this point. Now likewise, what we did in earlier cases, we also have to make a control volume and then analyze the problem. But here I feel that now you understand the meaning, the concept of control volume. So I have not drawn the control volume here, but I have tried to break the forces and the velocity vectors into components. And we use the same impulse momentum principle here. The net force in x direction is net change of momentum in x direction. So f of x is v out of the system minus v in into the system. That is nothing but f of x. Since f of x is negative direction, so I'm keeping it minus x is equal to, so going out, right? Going out means what is going out? This is going out. So rho q v cos theta, but sine, because of sine convention, I have to use minus, sorry, sine phi. Okay, this is the angle that is making when it leaves the plate. So phi minus this minus is coming from here, rho q, that is coming from the momentum coming into the system. So rho q is the mass times the velocity. Velocity in x direction is v cos theta, because this angle is considered to be theta. If the leaving jet and incoming jet makes the same angle theta, then everything will be theta. If it leaves at a different angle, then it will be, as you need this to be phi and this to be theta, and then accordingly we have to change. Now likewise, we use the same concept for y direction as well. Let's see, f of y I'm taking in this direction is equal to going out of the system. So rho q v sine phi is going out of the system minus rho q, that is v sine theta, is coming into the system in y direction. So I've just placed it here. So y, f of y is equal to this much. Now one more thing to understand here is, whatever the force that you have calculated right now is the force exerted by the vane on the control volume. Many a time question will be asked to find the forces exerted by the jet on the vane. Now the force exerted by the jet on the vane would be equal in magnitude, fx and fy. It will be equal in magnitude but opposite in direction. That is what we need to understand from here. Now, as a homework, I would like you to solve this problem. So if there is a jet, it is impinging on a curved surface and is leaving, making the same angle. Consider it is same angle. It is leaving the angle at theta, and it's also leaving the surface at an angle theta. You can solve for this. You can use the same principle like I did, and you will be able to solve this. With this, let's take a problem. As water flows out the 20 mm diameter pipe, it strikes the fixed vane. So this is a fixed vane. It's a circular vane. It's a semicircular, I think. It's just a vane, is a curved vane. Determine the resultant force on the vane needed to deflect the water 90 degree as shown. So what force is required to hold this so that the water gets deflected? So here we apply the same impulse momentum principle. Force exerted in any direction is equal to net change of momentum in that direction. So force in n direction is can be any direction. Okay, let's change momentum n direction. So f of x, okay, here let's start by drawing a control volume, right? So this is the incoming velocity, this outgoing velocity, and this is the force exerted by the plate on the vane, or by the plate on the jet, okay, on the control volume. So this is not what they're asking us to find. They're asking us to find the force exerted by the vane, by the jet on the vane. So it will be equal in magnitude to fx and fy, but opposite in direction. So likewise, we use the same concept, and finally, if we need to find the resultant force would be the square of f of x plus square of f of x, the whole square root. So this is the resultant force that is exerted by the plate on the jet, and the magnitude would be same. Okay, the direction would be opposite. The force that is exerted by the jet on the plate would be same in magnitude but opposite in direction. So with this, I'm ending the second part. We'll continue in next. Thank you.